Hi, it's Mr. T here. I'm going to go through and attempt the 2023 Level 2 Chemistry exam and hopefully give you some insight as to how we might approach different questions and how we answer them. Okay, so we can see here that it is 91165, demonstrate organic chemistry compounds. We're going to go down to question 1. Now, often this paper does start with a naming and a drawing part of the paper. So the first thing I notice is, let's see if we can name A. So in A, we've got 5 carbons in our longest chain. We have a chlorine coming off the first carbon. So this one here is going to be called 1-chloro pentane. Look at question B. It says it is methanoic acid. So we should remember here that this is going to have the carboxylic acid group because it's methanoic acid. And the meth means there's 1 carbon. So if I draw this here we go. Okay, so the next one is functional group here is NH2, that is an amine. So this, you can name this 2 ways. You can go amino to aminobutane, or you can go butane to amine. I'll write it down, butane to amine. There we go. And then the last one, propan 1-ol. Prop, of course, is 3 carbons, and then ol means that there is an OH group, or a hydroxy or alcohol functional group. So let's go and do that. 1, 2, 3, and coming off the first one. So I could either draw the OH on the left, or I could draw it on the right. Make sure that you do draw all of the hydrogens. I know it gets a bit tedious at times. And when you're doing these drawings here, I often will just do a fully expanded molecule and not the condensed form. Okay, so these molecules here are said to be liquids. This is question 2, room temperature. They want us to devise a procedure to distinguish between A to D using only litmus paper and acidified potassium permanganate. Right, okay, so what we see here is we have an haloalkane, a carboxylic acid, an amine, and an alcohol. So, what we should remember for a start is, let's draw these down. So, we've got carboxylic acid up here, we've got an alcohol, we've also got an amine, NH2, and I have a haloalkane, right? So, we've got a chlorine. Now, litmus paper, this one, blue litmus to red. Yep. This one, red litmus to blue. OH is going to react with the alcohol. Sorry, the propanoic acid is going to, propanoic acid. Permanganate, the acidified permanganate is going to react with the alcohol. And if we remember the color change, it's going to go from purple to colorless. Right. So what they want us to do is do a set of procedures. So I think it's going to be really easy for a start, just to say we're going to test all 4 samples with damp litmus. Because we're going to, once we've tested them all with blue and red, we're going to identify the base and the acid. So let's just move this up a wee bit and we'll see if we can answer here. Okay, so what do we say? To each sample, so we want observations, link to physical properties, give the structural formula. Okay, that's awesome. So we are going to say 2 to each of the 4 samples. The 4 samples. Test with. Now you need to make sure that the litmus paper is being put in water first, it's damp, or the solution has water. Damp litmus paper. Wait a minute, both blue and red. Okay, so that's fine. And what we would say here is the red one, blue litmus paper will turn red. The sample that turns blue litmus red, so this is our carboxylic acid, and our carboxylic acid was methanoic acid. Notice I've put down my observation and I've identified the molecule. So let's see if we can just move this up a bit more. So we'll keep going. So obviously the sample that turns the red litmus paper blue is the amine. Red litmus blue is 2. Oh no, we wrote this the other way, didn't we? Butan 2 amine. And remember, we're using these. We're looking at these as we're doing it. Okay, so these are the 4 we've identified. We've now identified 2 of them, so we have 2 left. That's the haloalkane and the alcohol. So we could do 2 tests here. Oh wait, there's 2 observations we note. So we're going to add acidified permanganate to the final 2 solutions. So let's add 10 drops of acidified potassium permanganate, so KMnO4. Let's put the N in there. Acidified, H+, add 10 drops to each sample. And heat. Now, interesting to note, when we add the potassium permanganate, what's going to happen is our let's have a look up here. So when we add it, a haloalkane will not dissolve, so we'll see 2 layers, but when we add the alcohol, it will dissolve, so we'll see 1 layer. We could use that as an explanation, but I'm actually going to use the explanation of how the permanganate oxidizes, and it's going to oxidize the alcohol, which was propan-1-ol, but it won't oxidize 1-chloropentane, right? So it will stay purple. The solution, sorry, not stay purple, will go colorless. That goes colorless, or goes from purple to colorless, because we have to be very clear with our observations. Is propan-1-ol. Okay, and then we had to draw a reaction if reactants and products, if there was any reaction occurring. This is a reaction. So we're going to draw propan-1-ol. Here we go. and put these hydrogens in. Perfect. And arrow. Let's write the reagent on top. Now, KMnO4 H plus. You can just write MnO4 minus H plus because the potassium and the permanganate actually dissociate when we put them in water. Either or, you have to be used to seeing them both ways. So this is going to actually form a carboxylic acid, the propanoic acid, and so we're going to draw that out, right? Remember, because we started with 3 carbons in the chain in propanol, then the acid form is also going to have 3 carbons in the chain. So last thing, the sample that did not, where the color did, where the sample where the purple color persisted, was pentan 1-ol. And there we have, we've used the 2 tests, well actually 3 if you take blue and red litmus as different tests. We have done that and we've identified what the 4 unknown compounds are. That's probably going to be an excellence question, that one. Okay, compound C. Okay, so if we go back up here, here's compound C. So we have to go back to this question. That's butan-2-amine. From the table opposite can be formed by reacting 2-bromobutane with a reagent. Okay, so we can see here what's happened. Let's have a look at this 2-bromobutane. Here it is. We've actually swapped out the bromine for the NH2. So they want us to write the name or chemical formula of the reagent required. So this is a substitution reaction. We're getting NH2, so we would have needed to add ammonia. That's NH3. And it has to be concentrated, or we usually say dissolved in alcohol. Let's tidy up that 3. Type of reaction that's occurring in this, well, we can see that the bromine is being substituted. So the Br is being replaced by the NH2 group. So this is a substitution. Reaction. Okay, let's just check that we've got everything they needed. Identify the type of reaction. Yep. Occurring to compound C and justify. Well, we've justified our choice by saying it swapped with the other one. So that's cool. Now, okay, compound A, they've drawn it again for us. Awesome. That's, remember, 1-chloropentane. Forms 2 different products when reacted with potassium hydroxide. Okay, so this potassium hydroxide here, when we see it, we realize here that what they're asking us is, do we know that potassium hydroxide reagent comes in 2 different conditions, either in aqueous, right? So we are going to have potassium hydroxide either looking like this, aqueous, or we add potassium hydroxide and we're going to produce the alcohol. Now remember, if we use it in aqueous, it's going to produce the alcohol functional group, and if we have it in alcohol, it's going to produce a double bond. Notice here, because the chlorine is on the end of the molecule, if we were going to do the potassium hydroxide alcohol, the double bond will only be able to form in one place, and that's coming off the first to the second carbon. So I have to give the conditions required for each reaction, state the type of reaction, and give structural formula for organic products. So what I'd really do here is I would do each one of these, explain them in turn, and then I would say the type of reaction and I'd draw the reaction. So if KOH, let's start with the first one I've got here, which is aqueous, is reacted with what do we call this? One chloro pentane. Then the Cl atom will be replaced by the OH group. I haven't said what type of reaction this is, but this is replacing, so I'm just going to state this is a substitution reaction. Cool. So I've covered the first bit. I've given the conditions. It's an aqueous. State the type of reaction. Done that. Let's draw the reaction. So here we have CH3, CH2, 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 CH2. I'm going to have to go on to the other side here. You'll better do this easier on a piece of paper than I am on here. So the reagent I added, remember, was KOH aqueous, and we said it did a substitution, so CH3, CH2, 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 OH. Cool. Let's just put these bonds in, so they're not going to ping me for not putting bonds. Give the structural formula. We don't have to name it, so that's fine. We could, though. We would just call it pentane 1-ol. So the next thing, if KOH alcohol is added, then an elimination reaction will occur. Now let's just give a quick rundown of what elimination reaction is. So we're going to say the double bond breaks, the double bond doesn't break. What am I writing? The double bond forms between the first carbon, or the number one carbon, first and second carbons after the OH group and hydrogen group from the adjacent carbon. There's only one. Okay, let's see if this makes sense. The double bond forms between the first and second carbons after the OH and the hydrogen from the adjacent carbon leave. Right, let's leave. Cool. So that's our explanation. We've written down that it's elimination, so that's cool. We just need to draw our reaction now. Let's start drawing this on the left-hand side, so I've got heaps of space. So CH3, CH2, 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 and Cl. Remember, this is the reagent, and in this case, it's dissolved in alcohol. So we are now going to go CH3, CH2, CH2, and then this is where it changes. I've removed a hydrogen off the second carbon here, and I removed the chlorine off the last, sorry, that's CH2, chlorine off the last carbon, or the first carbon, because we'd start numbering from that side. And that's how we answer this question. So just one more part here from question 1. Explain how you could distinguish between the different products of these two reactions. Okay, so in these two reactions, we had we produced an alcohol and we produced an alkene. So if we add bromine, Br2 aqueous, to both samples, and shake, then the one that's an alkene, which is pent 1-ene, then the pent 1-ene solution will change from orange or brown, depending on how strong it is, arrow, colorless. Explain how you could distinguish between different products of these two using, okay, so that's how we would do it. The sample that did not discolor straight away did not discolor straight away was pentan 1-ol. Now notice the first sentence here actually explains how I identified pent 1-ene, so we would know that the other one was pent 1-ol, but to be thorough, we should have also mentioned that pent 1-ol was reacted and it did not show any change. Okay, that's the first question finished. Let's see if we can get on to the next one. So the next one starts with a reaction scheme here. And we've got quite a complicated molecule at this top. This is called sodium hexanoate. So, and it says, is used to preserve foods, cosmetics, and medicines. An incomplete reaction scheme for the production of it from hexane to ol is shown below. Okay, so we're wanting to make it, here it is at the bottom, from these ones here. Now, from hexane 1-ol. I guess, oh, here's the question here. So we have to identify compounds E to G, reagents 1 to 3, and types 1 to 3, reaction types. Okay, well, let's just write this on here and then transfer it down to the bottom later. So let's see if we can work out what the compounds are. So the way that I would do this is here I can see that we have an OH, and the OH, we get two types of OH produced. Now the only way that we can have two different versions produced is if it's undergoing an addition reaction, and then we know that when we do an addition reaction to an alkene, we will, if the carbon is not on the end, we would have two different possibility of products. So I guess what I'm saying here, compound F is going to be an alkene, but the double bond of the alkene is going to either form at this place here or this place here, but it must form on the it must form on the right in order to produce an alcohol in the next step on the right and on the left, on the first or second carbon. So let me just demonstrate here. CH2, CH2, CH, CH2. Okay, so notice this is our first carbon, this is our second carbon. In order to actually undergo this addition reaction down here, okay, down here, we need to have produced an alkene. So this is the alkene we need to produce, because that's the only one that when we break the bond we can put an OH either on the first carbon or the second carbon, and that's what we have here. Okay, so if this is compound F, right, that is when the double bond, when the OH left and it took the hydrogen from the right hand side. This is actually going to be the minor product. The major product over here is going to be when I took the hydrogen from the third carbon, right? So if I take the OH away and hydrogen from the third carbon, this is my compound that I would produce. Okay, just 1 minute. I just need to get rid of that. Awesome. And let's go back to here. So, wait, one more bit. Let's get rid of you, number 2. Perfect. Okay. So, now I have this is CH3, CH2, and the double bond is going to go from this third carbon to the second carbon. There we go. And then the last compound is this one down here. Now what you need to remember is we form these carboxylate ions, or sodium hexanoate ions, from carboxylic acids. So compound C must be the carboxylic acid that has 5 carbons, because everything in the reaction scheme, because the starting product has 5 carbons in a row, must have 5 carbons in a row. So if I was to draw here we go, this is the carboxylic acid. Now we don't have to worry too much about this think too hard about when we draw it, because the carboxylic acid always has its functional group on the end of the molecule. Okay, so now we've identified the 3 organic products that we're missing from this scheme. Now what we can go through is do the reagents. So the first one, we're removing an OH and a hydrogen, which is essentially a water molecule. So they've already told us it's concentrated sulfuric acid. Let's go down to reagent 1. So reagent 1, I want to add to this pent 1-ene. I want to add a hydrogen and an OH group. So we're going to use the water in acidic conditions. So we can go H2O, H+. Sometimes the reagent for this is written H2SO4/H2O, but this is fine. The reagent to go from an alcohol to a carboxylic acid, well, you can choose 2. So you can do acidified dichromate, or you could do acidified permanganate, right? Remember, which is MnO4 minus H plus. Now, if you like to, if you want to put potassium dichromate, you put K2 CrO7/H plus. That's fine. You don't need to though. Reagent 3. So we have this carboxylic acid. How do I how do I get the sodium here? How do I change it into an ion? Well, we have an acid-base reaction here. So there's a couple of different ways I could. The easiest one for us to do here is just to add sodium hydroxide. So what happens when we add the sodium hydroxide is that this carboxylic acid donates or gives away its proton. So that's why it becomes a negative charge, and it gives it away to the OH and they become water, and the sodium just comes up and cozies up to the ethanoate ion. Okay, so that's our 3 reagents, and now we just need the reaction type. Okay, so we're going from our reagent to the our molecule at the top to F, so hexane 2-ol to F. We have removed, remember, an OH and a hydrogen, so this is an elimination reaction. And then down here, this reaction type, the carbon joined to the alcohol, when it turns into carboxylic acid, it makes 2 more carbon to oxygen bonds. This is oxidation. And I did say here that this was an acid-base reaction because we're adding sodium hydroxide, which is a base, and we had carboxylic acid, which was an acid. Now, if we got all of these correct here without any mistakes, okay, so mistakes would be things like we forgot to add the H plus to acidify it. Sometimes a mistake can be when we add something that has to be concentrated and we didn't write concentrated. So all perfect, you get an excellence. If you make, I think here 6 of them got you the merit and maybe 3 of them got you the achieved. Okay, so I would just transfer what I have done on the scheme here. In your actual booklet, you will have these 2 pages next to each other, so you can just fill it in as you go. So do you remember what the compounds were? Let's just do this quickly. CH3, CH, 2, CH, CH3. Okay, compound F was the other alkene, right, on the right. So this was one of the alkenes, the option we could take. So the alkene that formed the double bond from the 2nd to 3rd carbon, and then this is the alkene that forms the bond from the 2nd to the 1st carbon. Compound C was our carboxylic acid, CH3, CH2, 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 and carboxylic acid group. Now you can go around and just fill in all these wee bonds here, just to make it tidy. Look, often people who've done a lot of chemistry, they don't put the bonds in necessarily because they know that they're there, but I would recommend that you do it just to make sure you don't get a mark taken off. Okay, so the first reagent that we had to identify was that acidified dichromate, Cr2O7 2- H plus, or remember we could have used the permanganate. Reagent 2 was, let me just go up here and have a look at what reagent 2 was. Oh, I've got this around the wrong way. Sorry, let's correct this. I should have been looking at the same time. The first one was addition reaction. Okay, so for an addition reaction, we would write H2O, H plus, or sometimes it's written H2SO4, H2O. Okay, so any of those would have been fine. And remember, I just wrote this one down before. This is acidified dichromate or acidified permanganate. Reaction 3, we were adding a base. It had to have a sodium, so it was sodium hydroxide. You know what? You could have also added a carbonate, so you could have added sodium carbonate. That still would have produced the same ion. It just would have produced bubbles as well. The first reaction that we had to identify was the elimination reaction. The second was oxidation. And the third was the acid base. Okay, so it says the starting material. Can we explain why the starting material, this is it here, hexane 2-ol, I'll draw it here, is a primary, secondary, or tertiary alcohol. So we had 1, 2, 3, 4, 5. So really simple. It is not on the end of the chain, so it cannot be primary. It is not at a T junction of carbons. That means another carbon coming off here, so it's not tertiary. It is secondary. So we would say this is a secondary alcohol. And now we're going to give the reason. This is because the carbon, and this is the second carbon, right? That is bonded to the OH is bonded to 2 carbon atoms. So we try and be very clear and specific when we write these things. So I'm just going to put 2 here. This is my number 2 carbon, so they know which one. So I'm saying because that carbon number 2 is joined to the OH, then it is also bonded to 2 other carbons, and that's what makes it a secondary alcohol. Okay, so still going on with this theme. So the first 2 steps, the reaction where hexane 2-ol reacts with concentrated sulfuric acid, 2 products, E and F, are formed. Elaborate on the reaction. So what they want us to do is unpack here the 2 things. The 2 products that are formed, because what we're going to use here is Saytzeff's rule. Now, this is spelt many ways. Saytzeff's rule. Okay, and remember, Saytzeff's rule was the poor get poorer. But we can't write that down as a reason. This is just helps us remember. So get poorer. The poor get poorer. Explain 2 different products are formed. So we're going to explain this very simply. So we're going to say when the OH is removed by when the OH is removed by the concentrated H2SO4, a hydrogen atom from an adjacent means next to, adjacent carbon is also removed. So, and then we can, I'm just going to put 1 and 3. So, the double bond can either form between carbon 1 and 2. when the double bond forms, it can be between, wait a minute, between carbon 1 and carbon 2, or carbon 2 and carbon 3. Justify your choice of major and minor products. Identify the major and minor product. So the adjacent carbon that has the smallest, let's write smallest, or it's not smallest, is it? It's a least, let's just write least number of hydrogens attached will have its hydrogen removed the majority of the time. Now this is why we get this the poor get poorer, because we're taking, when we have two choices, remember, off the first and the third carbon up here. So actually this one here is poor because it only has 3 carbons, and this one here is rich because it has, the poor one has 2 carbons, and the one on the end is rich because it has 3. So the majority of the time we're going to take away the OH and the hydrogen from the third carbon. The minority of the time it's going to come from the other carbon. This forms pentan-2-ene. The hydrogen is removed from the first carbon the minority of the time. Or from carbon 1 the minority of the time. And producing or forming the pent-1-ene. Put a wee hyphen there. Cool. So 2 possible ones. We have to identify what the majority and the minority is. We explain why there's 2 different. So we really just dialed down and said, well, when we remove the OH, there are 2 adjacent carbons, so there are 2 options, right? And then we said one adjacent carbon has less hydrogens than the other, and we're going to remove the hydrogen from that carbon as well as the OH the majority of the time. And we'll do it from the other carbon the minority of the time. Give the structural constitutional isomer for hex 2-ene. That would only form 1 product. Okay, so if I was doing elimination and we only form 1 product, that happens when we have a symmetrical molecule. Right, see this one here? This is symmetrical. There's another H here. Let's draw that. Right, symmetrical molecule right down the middle. So sorry, that's wrong. Hexane 2. Okay, no, I just misinterpreted that. So this is, remember, we're removing it. So how do we make sure that it only happens from one place? Well, the way that we do that is really straightforward. We just choose a structural isomer of this that has the OH coming off the end, because when the OH comes off the end, we can only form the bond from the first carbon to the second carbon. right? There's no other options because there's only one carbon adjacent to the carbon on the end. So that's how we form only one product. Okay, question 3, last question of the paper. Polypropylene is polymer used to make web-like filters and N95 loose-fitting surgical masks. They filter out most microbes, but air can still go through them. So this is propylene. They want us to draw 3 repeating units. So what I would first advise you to do is I would redraw this. So I'm going to draw the double bond like that. I'm going to move this hydrogen to be vertical and the other hydrogen coming off the first carbon to be vertical. And then same thing for the hydrogen coming off the second carbon. And then this group here, I'm going to move to be vertical, and I condensed it at the same time to make it easier. So this is the basic building block, and I'm going to repeat that 3 times, but I'm going to remember to remove the double bond when I join them together. That's the only way they can. So I will essentially have hydrogen, CH3, hydrogen, and then I'm going to draw another one, right? It's a repeating unit, 3 of them. So I'm going to need 6 carbons. Now this type of case where they specifically tell you what to do, make sure you follow the instructions. If you don't, and then you only do 2, it's likely that they will not give you the marks for it, even though you know the knowledge and you've just misinterpreted it wrong. I just put a squiggly line at the end to say it continues. Why is this called addition polymerization? Okay, so, well, why is it called addition? We break the bond and reform a new bond. Well, sorry, the double bond is broken. And a new bond is formed. 2, a different atom is formed. So that's why it's called addition. Why is it called polymerization? Well, we took lots of individual units, so many individual molecules formed, bonded together to make a long chain. Now, of course, the long chain is called the polymer. The individual units, they are called monomers. So you can use those terms. So polypropylene is relatively chemically inert. That means unreactive substance. Compare the reactivity of polypropylene with its monomer. Remember, its monomer was propene. Linked to the structure of the monomer to its reactivity. So propene has a double bond it can undergo many different addition. Okay, so double bond is going to have addition reactions. And link the structure of the monomer. We'll just say polypropene only has single carbon to carbon and carbon to hydrogen bonds. so it is unreactive. Reactive, sorry, here. Okay, so this is good because it will not react with the air that you breathe out, so moisture in your breath. This is good. So the mask, wait, the polypropene in the mask will not react with water in from breathing. I mean, it could be a mist outside as well. So it won't fall apart. Because if we had a polymer and we broke parts of it, it would lose its structural integrity. It means it would start to fall apart, not break or fall apart, we'll say. So we just have to give one example. You could have said, oh, look, it won't react with chemicals in the air. So you have lots of different chemicals in the air that might react with things, but it won't if it's unreactive plastic. All right, geometric isomers. Okay, so we have to form a structure of a compound with the molecular formula C4H8 that forms geometric isomers. Okay, so geometric isomers, remember, is when we have a molecule with two different atoms coming off each carbon and a double bond, and the double bond stops rotation. So we have to draw the structure of your proposed compound in the box, state the requirements for a geometric isomer. Okay, so we don't need to draw it as cis and trans, but I will, because it's just easier to draw it, right? Because when they asked me to do drawings, if I was in a test to make sure that I can easily recognize I'll put the right number of bonds, I will draw it out as a full structure like this. Okay, so expanded molecule. Okay, so this one would be a cis, but we don't need to say that. So state the requirements for geometric isomers. Right, first the molecule must have a double bond. This prevents rotation. And holds groups atoms in a fixed position. Both carbons, and I'm going to label these as carbon 2 and carbon 3. Both carbons of the double bond must have two different groups or atoms, or substituents we can say, but we'll use groups or atoms, different groups atoms. Attached to them. And let's give a specific example to make sure we get excellence. In this case, the two different groups atoms are for carbon 2 and 3, They both have a hydrogen and a CH3 group attached. So basically how they're going to mark this is, if you draw it correctly, you'll get an achieved. If you explain how you if you explain the requirements, double bond, two different groups, atoms coming off each carbon, merit. If you can link it specifically to the molecule, like I did with the last sentence, you get excellence. Okay, structural isomers. Last question. Draw and name the 4 structural isomers. Okay, so here we already have 4 in a row, right? With the let's try another 4 in a row. I'm just going to draw the skeletons up here, so you can not put hydrogens in. So you can see this one here is different to our first one because this is called butan-2-ol. So anything that has a completely different name must be a structural isomer at least. 2-ol, okay, and we can just write this here. Now, let me just go over one thing to make sure that you don't make this mistake. I'll just draw this one out. I'm pretty confident this is one of my 3 answers. Okay, so you might think, oh, okay, so why don't we also put the OH coming off this one? Well, we could. Apart from this molecule here is just the same as the top molecule, it's just been rotated, okay? It's or flipped. So if you can imagine like a playing card, you just flip it over the other way. No matter what way we do it, the OH is always going to be off the second carbon, right? Because we always number from the closest side. Okay, so the next 2 isomers then can't have 4 carbons in a row, they must have 3. So we get 3 carbons in a row. We must have a carbon coming off the middle. So you might not see this, but actually these 3 carbons, this one here, this one here, and this one here, are all identical. They're all going to be CH3 carbons joined to the carbon in the middle. So I could put an OH off one of those carbons, but as soon as I put it off one of them, okay, then what happens is the other ones, I can't draw it coming off the other ones because they are essentially the same. Okay, so if I decide to draw an OH off here, putting an OH off another end carbon here is not different. It's just the same. You have to imagine that these molecules are actually in 3 dimensions. So we have a bond coming off here like, let's do this again. Carbon of a bond coming off here, which is my other carbon. I have one coming out of the page, looks like this, and I have one that goes into the page, right? So this is the shape, it's kind of a pyramid shape. So no matter where we take the OH off this, at any time I could just rotate it around and it would be the same as coming off one of the others. So there is only one, so that's one of the isomers. The other one actually though is we could put the OH coming off this carbon here, right? So we put the OH coming off there. So let's draw that. CH3, C, CH3, CH3, OH. Okay, by referring to the, oh wait, we haven't named these, so because I put that down the bottom, I'm going to identify the longest chain. This is it here, 3 carbons in a row. We have a methyl group coming off the second carbon, and this, remember, is an alcohol group, so it's coming off the first carbon. So this is going to be called 2-methyl propan-1-ol. This next one is longest chain here, right? Methyl group coming off the second. So notice this does have a different name, 2-methyl propan 2-ol. By referring to your compounds stored in the table, we'll explain why they are saturated isomers. Okay, so saturated means that we can't bond to any new atoms. All of these molecules contain no double bonds. No double bonds. Only single bonds. Single bonds. So no new bonds to extra atoms and groups can be added. Okay, and that's me. I've gone through the paper now. I'm just going to check that I've answered all the questions. Yep, so that's the end of the paper. So this has taken me about 1 hour. So if you're in a 3-hour exam, you have 3 of these papers. You should be able to do this a wee bit quicker than me if you're up to date with all of this, because you'll be drawing directly on paper. I'm just drawing on a tablet here next to me. It's a bit trickier, and I'm doing a lot of explaining along the way. Okay, so hopefully this has been helpful. Look out for the series of videos I'm going to do going through exams, and if you want to go through and watch these videos with me next time, just print off the exam and have a go, and then just check what I have to say about it.